All right. Back to those defining characteristics. So we're going to be looking at trig substitutions. So our defining characteristics for trig substitutions is going to be patterns. All right? Patterns, patterns, patterns. For a trig substitution, you do not start with trig. Ooh, surprising, right? When you do a trig substitution, you are not starting with trigonometry in your integral. We are going to sub in trig based on the pattern. Okay, so let's look at this. We have table 8.4 that we have where you start with the integral contains something. Then you are going to use the corresponding substitution. Then you have useful identities. Okay. 3. If I have a pattern of a squared minus x squared, all right, so that is my pattern. Remember way back whenever we had inverse trig and I'm like, oh, these patterns will come up again. Welcome. Welcome to that day. Woo, here we are. So a number squared first minus the variable squared. Now remember what happened when that variable was in the back. Which trig was that? Yeah, sine. So the same kind of thing. X is now equal to a sine theta. And that is going to be our substitution. All right. So a sine of theta is the substitution. And then we're looking at these and we have our trig identities that are going to help us out. So 1 minus sine squared theta is equal to cosine squared of theta. That's going to be a useful identity. All right. What happens if I'm adding them? A squared plus x squared. Which pattern is that? Yeah, tangent, right? That's the only one that is, oops. That's addition. Good. So then we use the Pythag identity that goes with that. 1 plus tangent squared is secant squared. Now, remember for secant when you had that inverse trig identity, you had that x out in front? Well, we're not worried about that for this one. We just want the pattern. And the pattern for this is x squared minus a squared. So if you start with your variable up front that's squared minus the number, then that's secant. So tune in. The variables in the back is sine. The variables up front, that's secant. Patterns, patterns, patterns. I can't express that enough. And then we're just going to rewrite this other trig identity, this Pythagorean that we used up above, because it still deals with secant, right? Secant squared minus 1 is tangent squared. All right. Okay. Let's try some on then, shall we? So here's our first one, which is example 2. We should have room for this one. These are rather long also, so just heads up on that. But we should be okay here. Example 2. I want to oh my. Well, there we go. I want to integrate dx over 16 minus x squared to the 3/2 power. What pattern is that? Sine. You see that? Here, if I have the squared of a number that's squared is up front, the variable is in the back. So I'm going to see this pattern. First of all, okay, wait. Let me time out and back it up. Can I do a U substitution? No, right? U substitution is not happening here. So I cannot do a U substitution. If I can't do a U substitution, then we look at the patterns. And this pattern leads us to a trig sub because it's squared minus squared. Okay, so I now look at this and I say x is equal to a, which a in this instance is a 4, right? 4 sine of theta. So the derivative of that is going to be good for cosine theta, d theta. You are changing variables and you're not going back. So I harp on you, harp on you, harp on you. Commit to that u sub, commit to a substitution. You're going to have problems where you can't go back. There is no going back for that. Here, welcome. Welcome to this problem right here. It was coming, and I told you it was coming, and we made it. So that should make you happy. I am switching my variable from an x to be in terms of theta. All right? Okay. Everywhere you see x, you're going to put a 4 sine theta. Everywhere you see dx, you're going to put 4 cosine theta d theta. I'm going to scoot this up a little bit. So I am actually integrating here from 4 cosine theta d theta in my numerator, because that's my dx, over 16 minus, now I am taking this and squaring it. So it's 16 sine squared theta, and then that whole thing is to that 3/2 power. You see that? Okay. Now you've just subbed it in. Now I'm doing everything in terms of theta. I've got my d theta here. Simplify this out. That's what we're doing, is simplifying this out. So I'm going to scoot this up. And I am going to bring this 4 out front. Oops, 4. And then I have cosine theta over. When you have this 16, I can factor out that 16, but it stays with this exponent. So when you factor that out, I actually have 16 to the 3/2 power. And then I have 1 minus that sine squared theta to the 3/2 power. And this whole thing is to d theta. Do you see that? I'd be smart about this. This 2 over here means square root, right? This is really 4 over 4 cubed. So this is 1 over 4 squared. And then I have cosine. I'm going to squeeze this down. Remember how we said, oh, there's some useful identities. And there it is, right? 1 minus sine squared is equal to cosine squared, so we're going to use that identity here. Let's do it right now. I now have cosine of theta. I don't know why that's doing that. Over cosine squared theta to the 3/2 power d theta. All right? I'm square rooting something squared. So this 2 cancels out that 2. And so it's cosine over cosine to the 3rd power. Do you see that? So one of these cosines takes out of those 3 and just leaves me with a 2. So I've got 1/16 out front of 1 over cosine squared theta d theta. Do you see that? So that's just simplifying. So the square and the square root cancel and leaves me with a cosine cubed in the denominator. So one of the cosines from the numerator takes out that cube, just leaves me with a squared. Then we use identities. 1/16 here, and I end up with secant squared theta d theta. We know that antiderivative, don't we? I'm going to bring it on up here. I thought I had room. I'm going to rewrite this just so that we've got it all together. 1/16 of secant squared theta d theta. And tangent. Now here's the deal. I end up with tangent as an answer. My problem started in terms of x. This is an indefinite integral. When you have an indefinite integral, then you have to convert back to the original variable, right? And we are going to do that with right triangle trigonometry. This is the same thing as x over 4 is equal to sine of theta. SOHCAHTOA, right? Opposite over hypotenuse. So from theta, I have opposite, which is x, over my hypotenuse here, which is 4. Then you can go through and use Pythagorean theorem. I'm going to put question mark here. So question mark squared plus x squared is equal to 4 squared. And look what's happening. Question mark here, squared is equal to 16 minus x squared. Have you seen this before? Oh, hello, original pattern. And that's going to happen every single time. These are sides, so I'm not doing plus or minus. I want the principal root. So my angle is really, or my side length is the square root of 16 minus x squared. The square root of 16 minus that x squared. All right. So we go to right triangle trig. So we're making a substitution. We're going to right triangle trigonometry. And now I'm looking at tangent. And tangent, right, for SOHCAHTOA is opposite over adjacent for my tangent. So I've got opposite over adjacent. So I have 1/16 times my opposite, which is x, over my adjacent, which is 16 minus x squared, plus c. So you could put those together. You can leave it out. I don't care if you put x over 16 square roots of 16 minus x squared plus c. That's good. All right. So here's the deal when it comes to trig sub. You find a pattern, substitute in for theta with your trigonometry. Then at the end, to put it back in terms of x, you have to do your right triangle trigonometry. Now, if it's a definite integral, which is legit, then you don't ever have to go back with your right triangle trig, right? Because once you commit, then you've totally committed. Okay, we're going to do some more.